In the late wet season of 2019, a ranger working a remote stretch of the Northern Territory in Australia discovered the partially consumed remains of a large feral pig on the bank of a tidal creek. The animal had not been shot, it had not drowned. The cause of death, confirmed by the bite radius and the drag marks that led from the water's edge into the shallows, was a saltwater crocodile. None of that was remarkable. Saltwater crocodiles kill feral pigs with regularity across the top end, and the evidence of those kills is a routine feature of the landscape. What the ranger noted in his field report, and what eventually filtered into a research context, was the timing. The kill had occurred during a rainstorm, not after a rainstorm, during one. The ranger had been close enough to the creek to hear the rain hammering the water surface when the disturbance occurred. The crocodile had not waited for the rain to stop. It had moved while the rain was at its heaviest, in conditions of severely reduced visibility and dramatically elevated ambient noise, and it had made a successful kill in water that was churning with the impact of heavy rainfall. The ranger had been in the territory for 11 years. He had written dozens of field reports. He noted the timing not because it surprised him in any fundamental way, because anyone who has spent time watching saltwater crocodiles develops a working intuition that these animals exploit rain, but because he had begun to notice the pattern recurring with a frequency that seemed to exceed coincidence and that no one had formally quantified. He mentioned it to a researcher he knew at Charles Darwin University. That conversation eventually contributed to a line of inquiry that is still being developed, but that has produced findings that reframe something fundamental about how saltwater crocodiles select their ambush timing. What the research is pointing toward is not simply that saltwater crocodiles attack more during rain. The popular observation of that correlation has existed for as long as people have lived alongside these animals. What it is pointing toward is why, mechanistically and specifically. And the answer involves a sensory system so precisely calibrated to the acoustic properties of falling rain that the word ambush begins to feel inadequate for what saltwater crocodiles actually do. They are not merely waiting for cover. They are responding to a signal. Rain, in the acoustic environment of a saltwater crocodile, is not weather. It is a trigger. If you find this kind of deep examination of predator behavior as compelling as I do, the kind that goes beneath the surface observation and into the actual biology, consider subscribing. This channel exists to do exactly this kind of work, and there is a great deal more of it coming. To understand why rain functions as a trigger rather than simply a condition, you need to understand the sensory architecture of the saltwater crocodile with a level of precision that most popular treatments of these animals never reach. The saltwater crocodile, Crocodilus porosus, is the largest living reptile on Earth. Adult males in the Northern Territory and in Papua New Guinea regularly exceed 5 meters in length and can approach or surpass 1,000 kilograms in body mass. They are the apex predator of every ecosystem they inhabit, from tidal estuaries to freshwater billabongs to open coastal waters. And their behavioral sophistication is, in the context of reptile cognition, extraordinary. But it is their sensory biology that makes them unique among large predators, in a way that has direct relevance to the rain ambush phenomenon. Saltwater crocodiles, like all crocodilians, possess a sensory system that has no precise equivalent in any other living predator. Distributed across their head, jaw, and body are thousands of small, dome-shaped structures visible to the naked eye as tiny raised spots embedded in the scales. These structures are called integumentary sensory organs, and they are among the most sensitive mechanoreceptors found in any vertebrate animal. The term mechanoreceptor means a sensor that detects mechanical force, specifically pressure, vibration, and displacement in the surrounding medium. Integumentary sensory organs in crocodilians detect disturbances in water with a sensitivity that is difficult to overstate. They can resolve the direction, distance, and in some cases, the source characteristics of pressure waves generated in water at distances and with a precision that rivals or exceeds the lateral line systems of fish, which are themselves among the most sensitive pressure detection systems in the animal kingdom. The integumentary sensory organs are concentrated most densely around the jaw margins, where their sensitivity is highest and where they are most precisely positioned to analyze pressure waves approaching from different directions. Research conducted on American alligators, which share the basic sensory architecture of Crocodylus porosus and have been studied more extensively due to their accessibility, has demonstrated that these structures can detect pressure waves generated by a single water droplet striking the surface at a distance of several body lengths. A single drop. The sensitivity is on the order of what a human would experience as a barely perceptible vibration, and it is directionally precise enough that the animal can orient toward the source without visual confirmation. Now consider what rain does to that sensory system. When rainfall strikes a water surface at any meaningful intensity, the acoustic and pressure environment of the water is transformed. The surface is being struck by hundreds of thousands of individual impacts per second across the entire area of the body of water. Each impact generates a pressure wave. Each pressure wave propagates outward from its point of origin. The cumulative effect is a noise field of extraordinary intensity and spatial density, filling the water with overlapping, interfering pressure waves from every direction simultaneously. For an animal that detects prey through pressure wave analysis, this is the acoustic equivalent of a whiteout. The signal-to-noise ratio collapses. The precise directional and distance information that the integumentary sensory organs normally deliver to the nervous system is buried under the storm of rainfall impacts. The animal is effectively deafened in its primary detection modality. This would seem, on first consideration, to be an argument against rain as a favorable hunting condition. If the crocodile's most sensitive sensory system is overwhelmed by rainfall, why would rain increase its predatory success? The answer is the key to everything, and it lies not in what the rain does to the crocodile, but in what the rain does to everything else. Every animal that lives in or near the water bodies inhabited by saltwater crocodiles, every prey animal, and every potential prey animal faces the same acoustic disruption that rain imposes on the crocodile. The difference is that prey animals use sound as a primary threat detection system, and the rain does not simply disrupt their ability to hear approaching threats. It actively masks the acoustic signature of an approaching crocodile with a blanket of competing noise at precisely the frequencies that would otherwise alert them to danger. A wallaby drinking at a creek bank on a clear night is operating in an acoustic environment of very high signal clarity. The sounds it needs to detect, the displacement of water by a large body moving through it, the subtle disturbance of vegetation at the water's edge, the characteristic low-frequency pressure wave that precedes a crocodile's approach lunge, all of these are distinct and detectable above the background noise level of the environment. The wallaby's auditory system, its hearing, is calibrated to a level of sensitivity appropriate to an environment where these sounds are recoverable above background. Wallabies, like most mammals, have highly developed hearing in the frequency ranges that matter most for predator detection. Under normal conditions, in a quiet environment, a large animal moving through shallow water generates a detectable acoustic signal at distances that give the prey animal time to move away before the attack can be completed. Rain eliminates that margin entirely. The masking effect of rainfall on the acoustic signature of an approaching crocodile is not a partial reduction. At moderate to heavy rainfall intensities, The pressure and sound environment at the water surface is so thoroughly disrupted that the acoustic signal of even a large crocodile moving at speed becomes essentially undetectable against the background. The prey animal's threat detection system has been rendered non-functional. At the same moment, the predator's primary sensory disruption has also occurred. This sounds like a symmetric disadvantage, and in a narrow sense it is. Both animals are operating with degraded sensory information. But the asymmetry is in the strategic consequences of that degradation, and the asymmetry is enormous. The crocodile does not need its integumentary sensory organs to complete an ambush attack on a prey animal that is already at the water's edge. It needs them for the detection and approach phase. Once the crocodile is already in position, already submerged in the shallows adjacent to a drinking site or a crossing point, already within attack range, the integumentary sensory organ system is less critical because the attack is no longer a search problem. It is an execution problem. The crocodile already knows where the prey is. It is watching with eyes positioned at the top of its head, which remain above water even when the rest of the body is fully submerged. It is feeling the substrate vibrations of the prey animal's footfall with whatever body surface is in contact with the bottom sediment. At close range, in position, the crocodile's other sensory systems, vision, substrate vibration detection, even the deep mechanosensory channels that operate at the lowest frequencies, are sufficient for timing and executing an attack. The prey animal, by contrast, has lost its primary defense precisely when it most needs it, specifically during the approach to water, in conditions where its guard would otherwise be highest. Prey animals in saltwater crocodile habitat are not naive about the risk the water represents. They approach drinking sites with caution. They scan. They listen. They do not hold their position at the water's edge for longer than necessary. This behavioral wariness is calibrated to normal sensory conditions. Rain decouples the behavioral wariness response from the actual risk level. The prey animal listens and hears nothing alarming. It sees nothing alarming. The rain is covering both the acoustic and, to a meaningful degree, given the surface disturbance, the visual evidence of the crocodile's presence. The animal that would have detected a threat and retreated under clear conditions approaches with its threat assessment returning a false negative. The crocodile is there. The crocodile has been there, potentially, for a very long time. The prey animal's sensory systems are simply no longer able to tell it that. The phrase, "a very long time," is not rhetorical. This is where the behavioral dimension of the rain ambush phenomenon becomes as important as the sensory dimension, and where the picture of saltwater crocodile intelligence that emerges is one that most people, even people who have spent time studying these animals, find difficult to fully accommodate without resistance. Saltwater crocodiles do not simply exploit rain when it happens to catch them in position near prey. The weight of observational evidence from researchers and experienced field workers across northern Australia, Papua New Guinea, Indonesia, and Malaysia, combined with the small but growing body of formal behavioral research, points toward a behavioral pattern that is genuinely prospective. These animals position themselves in anticipation of rain. Not all individuals, not all the time, not in every context. But the pattern of positioning behavior observed in large adult saltwater crocodiles in well-studied habitats is inconsistent with random foraging movement modified opportunistically by weather. It shows characteristics of deliberate pre-event staging. The evidence for this is behavioral rather than neurological, which means it requires interpretation, and interpretation of crocodilian cognition always risks anthropomorphic projection on one side and reflexive denial of any planning capacity on the other. The research community, working on crocodilian cognition, is careful about both traps, and the language that has emerged from that community is precise. What researchers describe is not planning in the human sense, not deliberate conscious projection into a hypothetical future scenario. What they describe is associative learning that operates on temporal and environmental cues to produce behavioral outputs that function, in their outcomes, identically to planning. Saltwater crocodiles are long-lived animals. Individuals in the wild may survive for 60 to 70 years. They inhabit the same territories for decades. They feed from the same ambush sites across seasons and years. The learning that accumulates over a lifetime in a fixed territory is not trivial. A large, adult male saltwater crocodile that has occupied a stretch of tidal creek for 25 years has experienced thousands of days of weather and thousands of interactions between weather and prey behavior. Its nervous system, which despite the popular dismissal, is substantially more sophisticated than the cold mechanistic machine the phrase reptile brain implies, has been integrating that information continuously. The association between specific meteorological cues, dropping barometric pressure, changing wind patterns, specific cloud formations visible from a partially submerged position, increasing humidity, and the subsequent occurrence of rain, and between rain and the behavior of prey animals at water access points, is not an association that needs to be consciously understood. It needs only to be reliably encoded in behavioral tendency through the mechanisms of associative learning that all vertebrates possess. What the research is finding, and what the field observations are accumulating to support, is that experienced adult saltwater crocodiles respond to pre-rain meteorological cues by increasing their positioning behavior at high-value ambush sites. They move into position before the rain arrives. They hold position longer during and after rain than they do in comparable periods of clear weather. They are more likely to be found in shallow water ambush positions at drinking sites and crossing points during periods of rainfall and in the hours immediately preceding and following rain than during extended clear periods. This is not a trivial behavioral observation. It is a description of an animal that is responding to environmental signals that predict, rather than coincide with, favorable hunting conditions. Whether you call that planning or sophisticated associative prediction is partly a semantic question. The behavioral reality it describes is the same. The temporal dimension of this behavior, how long crocodiles will hold a position in anticipation of prey, is one of the most striking aspects of the rain ambush phenomenon and one of the most important for understanding the risk these animals pose to humans who encounter them in rainy or pre-rain conditions. Saltwater crocodiles are the most patient predators in the world in any absolute sense. The metabolic consequences of immobility for a reptile are radically different from those for a mammalian predator. A lion that fails to make a kill for 4 days is in physiological trouble. A saltwater crocodile that holds a position motionless for 4 days has barely drawn down its energy reserves. The ectothermic metabolism that critics of crocodilian sophistication sometimes use as evidence of their limitations is simultaneously the source of their extraordinary capacity for protracted ambush. They can wait. They can wait in a way that no mammalian predator can replicate. And during rain, with the acoustic cover that rainfall provides, and with the increased movement of prey to water sources that often accompanies rain events in the seasonally dry environments of northern Australia, the expected return on that wait increases dramatically. Field researchers who have conducted long-term observations of marked individual crocodiles have documented animals holding ambush positions at specific sites for periods extending to multiple days, when conditions, including weather patterns, consistent with impending or ongoing rainfall, are favorable. The same sites, the same individuals. The same pattern of extended positional commitment when meteorological conditions predict rain. The data is not yet systematized to the degree that a formal meta-analysis could be published with precise effect sizes. But the directional consistency across independent observers in geographically separated study areas is high enough that dismissing it as anecdotal would misrepresent the current state of the evidence. The prey concentration effect of rain, which operates alongside the sensory masking effect and combines with it to produce the elevated attack success that researchers and indigenous land managers have observed for generations, is worth examining in specific detail because it is often discussed superficially and its mechanism is not intuitively obvious. The common explanation is that rain brings animals to water to drink, and while this is true, it is an incomplete account of what actually happens to prey behavior during rain events in the ecosystems saltwater crocodiles inhabit. Northern Australia's top end operates on a seasonally extreme hydrological cycle. The wet season, from approximately November through April, delivers the overwhelming majority of the region's annual rainfall in concentrated, intense events, often associated with monsoon circulation. The dry season reduces surface water availability to a small fraction of wet season levels. In late dry season and early wet season, the transition period when the first meaningful rain events begin to occur after months of desiccation, the behavior of prey species in saltwater crocodile habitat undergoes a shift that has direct relevance to crocodile predation. The late dry season concentrates prey species at the diminishing water sources that remain accessible. Wallabies, agile wallabies, and antilopine wallaroos in particular concentrate around permanent or semi-permanent waterholes and creek pools with a density that is not observed during the wet season when water is available everywhere. This concentration is itself a predation opportunity that saltwater crocodiles exploit heavily, and the kill rates at waterholes in late dry season reflect it. But the early wet season, the period when the first rains arrive after this long dry, produces a specific behavioral response that is distinct from the dry season concentration pattern and that carries its own predation significance. When the first heavy rains of the approaching wet season arrive, prey animals that have been restricted in their movements by water scarcity begin to move. They move to assess new water sources. They move along drainage lines where sheet flow is beginning to accumulate. They move to areas of vegetation that have been dry for months and are now producing fresh growth in response to rain. This movement is often in conditions of reduced visibility and elevated ambient noise produced by the rain itself. And it is often directed toward or across the water bodies and drainage channels where saltwater crocodiles are waiting, with a behavioral regularity that experienced crocodiles can anticipate because they have seen it before, in the same places, in the same conditions, at the same point in the annual cycle, for potentially decades. The combination of concentrating prey, acoustic masking from rainfall, reduced visibility in rain, and associated low-light conditions, and the established ambush positioning of experienced crocodiles that have spent weeks or months in the same territory, produces a predation environment that represents the closest thing in the animal kingdom to a system specifically optimized for a single predator. The saltwater crocodile did not design this system, but it has been shaped by evolutionary time and refined by individual learning to exploit it with a precision that no other large predator on Earth can match in its specific operational context. The acoustic component of rain as a trigger deserves a more detailed examination because the research on crocodilian hearing, which is less well known to general audiences than the integumentary sensory organ work, adds a layer to the rain ambush mechanism that is as important as the masking effect. Crocodilians are not the silent animals they are often portrayed as. They are among the most acoustically active reptiles in the world. They produce sounds for communication, for territorial signaling, for reproductive advertisement, and for mother-young interactions that begin before the eggs hatch. The ability to produce and detect specific sounds is wired into their biology at a level of sophistication that their evolutionary lineage, which predates the mammals by a substantial margin, has had an enormous amount of time to refine. Crocodilian hearing is mediated by a tympanic membrane system that is structurally different from mammalian hearing but functionally capable across a broad frequency range. Research on frequency sensitivity in crocodilians has established that they hear well across the range, from approximately 50 Hz to around 8,000 Hz, with peak sensitivity in a range that encompasses the frequencies produced by the movements of large prey animals in water and on land. The low-frequency channels of crocodilian hearing are particularly relevant because they overlap with the frequencies produced by large animals walking on saturated ground, by disturbances in shallow water, and by the vocalizations of prey species. Rain produces sound energy across a very broad frequency spectrum. Heavy rainfall generates significant energy in the low-frequency range, specifically in the band below 1,000 Hz, where the impact of large raindrops on the water surface and the associated disturbance of shallow water produces pressure waves that propagate both through the water column and as airborne sound. This low-frequency component of rain noise occupies the same frequency band as the sounds produced by prey movement. The masking effect of rain on prey-generated sound is therefore not merely a function of overall noise level. It is a frequency-specific masking at the frequencies the crocodile would otherwise use to detect prey, which makes it qualitatively different from, and more complete than, a simple reduction in signal strength. There is a secondary acoustic effect of rain that has received less attention, but that may be equally important for understanding the trigger mechanism. The sound of rain on a water surface has a spectral signature that is distinct from silence, from wind, from flowing water, and from the sounds of prey movement. It is broadband, relatively uniform in spatial distribution, and highly consistent in its temporal pattern at any given intensity. A crocodile that has experienced many rain events over many years has, through associative encoding, a very precise template of what the rain soundscape sounds like. And critically, it has a precise template of what prey movement sounds like within that soundscape, because it has detected and responded to prey movement during rain events. Research on the auditory masking and unmasking capabilities of crocodilians in naturalistic conditions, which is still in relatively early stages, is beginning to suggest that these animals may maintain a capacity to extract certain prey-specific signals from within the rain noise field that their sensory systems would struggle to detect in other masking conditions. The integumentary sensory organs may be more selective in their frequency sensitivity than previously understood. If the mechanoreceptors that compose these structures have peak sensitivity at frequencies that correspond to the pressure signatures of large animal movement in shallow water, rather than uniform sensitivity across the broadband noise spectrum of rain, then the rain noise field would produce less complete masking of prey-generated signals than a naive calculation of signal-to-noise ratios would suggest. The crocodile's primary detection system might be disrupted by rain at the frequencies of distant prey detection, while remaining partially functional at the shorter range frequencies most relevant to triggering an attack response. This is speculative in the sense that the specific frequency sensitivity curves of integumentary sensory organs have not been fully characterized across the relevant range. But it is speculative in a direction that is supported by the functional evidence of attack success in rain, and it is a hypothesis being actively tested. What this means, practically, is that rain may not merely be a passive acoustic blanket that benefits crocodiles by hiding them from prey. Rain may generate an acoustic environment that is specifically navigable by crocodilian sensory systems in ways it is not navigable by the sensory systems of prey species, because crocodilian sensory evolution has been occurring in rain-inclusive environments for a time frame measured in the tens of millions of years. The crocodile lineage is among the oldest surviving vertebrate lineages on Earth. The family Crocodilidae, to which Crocodylus porosus belongs, has been present in essentially its modern form for approximately 85 million years. The monsoon rainfall regimes of tropical and subtropical Asia and Australia, the primary geographic range of the saltwater crocodile, have been a consistent feature of those environments across enormous stretches of geological time. The evolutionary pressure to exploit rain as a hunting condition, rather than simply tolerating it, has been operating on crocodilian biology for longer than mammals have existed in any recognizable form. This temporal context is important because it reframes the rain ambush behavior from a learned behavioral flexibility to something with deeper evolutionary roots. The behavioral flexibility, the associative learning, the individual refinement of ambush site selection and timing is real and is documented. But the sensory substrate on which that learning operates, the integumentary sensory organs tuned to water disturbance, the auditory sensitivity calibrated to the low-frequency range of prey movement, the neurological integration of multiple sensory channels in a way that produces functional situational awareness in conditions of high noise, did not emerge from individual learning. It was built, over millions of years, in environments where rain was a recurring feature of the predation landscape. The saltwater crocodile is not a primitive holdover from a simpler time. It is the product of longer, continuous evolutionary refinement than virtually any other large predator alive, and the rain ambush behavior is, in part, the expression of that refinement. The human dimension of this phenomenon requires careful and honest treatment, because saltwater crocodile attacks on people are not the hypothetical or historical category they are sometimes presented as. They are a current and ongoing feature of life in the regions these animals inhabit, and the rate of fatal attacks in some of those regions is not trivial in any meaningful sense. Globally, saltwater crocodiles kill somewhere between 200 and 300 people per year, based on the best available estimates, which are hampered by significant underreporting in rural and remote areas of Southeast Asia, Papua New Guinea, and parts of Indonesia and Malaysia. Some analyses suggest the actual toll may be higher. The Northern Territory of Australia, which has the most rigorous reporting system and the most thoroughly studied population, averages 1 to 3 fatal attacks per year from a human population base of less than 250,000 people in the relevant inhabited zone. That is an attack rate that is not comparable to any large predator in North America or Europe, and that constitutes a genuine and specific hazard to the people who live and work in saltwater crocodile habitat. The rain connection to human attacks is not statistically isolated in the way it would need to be to declare it formally characterized, but the reported circumstances of fatal saltwater crocodile attacks in northern Australia show a pattern that is consistent with the rain ambush mechanism. A disproportionate number of fatal attacks have occurred during or immediately after rain events. A disproportionate number have involved people approaching water at night or in low-light conditions during wet season weather. A disproportionate number have involved people doing things that prey animals do under equivalent conditions, approaching water, crossing water, working at the water's edge, during periods when the acoustic environment is disrupted by rain and the crocodile's positional advantage is greatest. The cases that have been examined in the most detail by researchers and by the Northern Territory government coroner, who has conducted inquests into a number of saltwater crocodile fatalities over the past 2 decades, consistently reveal the same structural features. The victim was near water. It was raining, or conditions were consistent with recent heavy rain. There was reduced visibility. The crocodile was not visible before the attack. The attack was sudden, from very short range, with no prior behavioral warning detectable by the victim. The crocodile, in the reconstructed scenario, had been in position at the attack site before the victim arrived. These are not the characteristics of a random encounter between a wandering crocodile and an unlucky human. They are the characteristics of a completed ambush by an animal that was in position and waited. The indigenous land managers of northern Australia, the Aboriginal communities whose relationship with saltwater crocodiles is both ancient and specific, have a detailed body of knowledge about the conditions under which these animals are most dangerous, that predates formal research by a period that is difficult to measure precisely but is certainly long. The traditional ecological knowledge held in communities across Arnhem Land, the Kimberley, and the Top End includes specific guidance about rain and crocodile behavior that aligns with what the formal research is now beginning to document. The knowledge is not framed in the language of sensory biology or acoustic masking. It is framed in the language of behavioral observation, accumulated across generations of careful attention to the same animals in the same places. Rain makes them more dangerous, not because it brings them out. They are present in and near the water, regardless. Because it changes what they do when they are there, and because it changes what you can know about what they are doing before it is too late to act on that knowledge. This convergence between traditional ecological knowledge and formal research findings is worth noting not as a rhetorical gesture toward cultural sensitivity, but as an evidentiary point. When two completely independent knowledge generation systems, one built on millennia of direct observational accumulation, and one built on the methodological framework of modern biology, arrive at the same conclusion about the same phenomenon, the confidence with which that conclusion can be held increases substantially. The rain ambush behavior of saltwater crocodiles is not a novel discovery by either framework. It is a fact about these animals that has been known to the people who live among them for as long as the people have been there. What is new is the mechanistic explanation that is beginning to emerge from the sensory biology research. And what is new is the precision with which that explanation maps onto the behavioral observations that field researchers and indigenous knowledge holders have accumulated independently. The spatial ecology of the rain ambush behavior, specifically the question of how saltwater crocodiles select and return to specific ambush sites, is another dimension of this phenomenon that the GPS telemetry research of the past 15 years has illuminated in ways the earlier literature could not. Saltwater crocodiles are not random movers within their territories. They are highly site-faithful, returning to specific locations with a consistency that reflects detailed spatial memory. Large adult males in the Northern Territory study populations have been tracked showing repeated returns to specific creek bank positions, waterhole margins, and estuarine crossing points across multiple seasons and multiple years. The site fidelity is not merely a product of territorial exclusion, not simply the outcome of being prevented from going elsewhere by competitors. It is expressed in the precision with which individuals navigate back to specific locations within their established territory, locations that, when examined in terms of their physical characteristics, share features associated with high predation success. High-value ambush sites share a characteristic set of features that researchers have begun to formally catalog. They are typically at or near established prey movement corridors, paths that prey animals use repeatedly to access water. They offer the crocodile a submerged approach angle that minimizes detection risk. They have water depth profiles that allow a large crocodile to achieve complete submergence with minimal surface disturbance. They are often adjacent to areas of bank structure, undercut roots, overhanging vegetation that provide visual concealment of the crocodile even at very close range from the bank. and they are spatially positioned relative to the direction of prevailing water flow in ways that minimize the downstream detection of the crocodile's body odor or physical displacement by approaching prey. A crocodile returning to one of these sites during or before rain is not simply finding water to rest in. It is precisely reoccupying a position whose spatial and structural properties have been validated by previous experience as functionally superior for ambush. The return to a known high-value site under conditions of acoustic masking produced by rain represents a compounding of advantages. The site is good. The conditions are good. The crocodile knows the site is good because it has used it before. The combination of a spatially optimized position and acoustically optimal conditions is not coincidental. It is, in the functional sense, a strategy. The use of that word, strategy, will trigger objections from some corners of the vertebrate behavior research community, and those objections deserve to be engaged rather than dismissed. The objection to attributing strategy to a crocodile is not merely semantic. It is a substantive claim about the cognitive architecture required to produce behavior that looks strategic, and whether that architecture is present in a crocodilian brain. The classical position in the field has been that reptile cognitive architecture, while adequate for conditioning and associative learning, lacks the executive and prefrontal structures associated with deliberate planning and strategy in mammals. This position is not simply a prejudice. It is grounded in comparative neuroanatomy. Crocodilian brains do not have the neocortical structures that are associated with working memory, planning, and deliberate goal-directed behavior in mammals. This is anatomically true. What the classical position underestimates, and what more recent work in reptile cognition has been systematically correcting, is the degree to which the absence of mammalian cognitive structures does not imply the absence of the functional capacities associated with those structures. Comparative cognitive research over the past 20 years has found repeatedly that the functional capabilities ascribed to specific neural structures in mammals can be achieved through different architectures in other vertebrate lineages. What matters, from a behavioral ecology perspective, is not whether a saltwater crocodile thinks about the rain the way a human hunter might think about it, considering and planning and projecting into the future with deliberate, conscious intent. What matters is whether the behavioral output produced by the crocodile's nervous system in response to rain predictive cues is functionally equivalent to what a deliberate planning process would produce, and the evidence strongly suggests that it is. The crocodile does not need to understand rain to respond to rain. It does not need to consciously calculate the acoustic masking properties of rainfall to move into position before rain arrives. It needs a nervous system that has encoded the association between specific pre-rain cues and subsequent predation success strongly enough that those cues reliably drive positioning behavior. The functional outcome, an animal in the right place at the right time under the right conditions, is identical whether it was produced by deliberate planning or by sophisticated associative conditioning. The prey animal that encounters it does not receive a more survivable attack because the crocodile was responding to conditioning rather than conscious intent. The implications for human safety in saltwater crocodile habitat are direct. The rain ambush phenomenon means that the risk profile of any human activity near water in saltwater crocodile habitat changes dramatically with weather. The animal that was not present at the water's edge yesterday, or that was present but passive, may have moved into a precise ambush position in anticipation of or during rainfall. The acoustic conditions that rain creates mean that the human approaching water in the rain cannot rely on the detection cues, the water disturbance, the low-frequency pressure waves, the surface ripple of a large submerged body, that they might detect under calm conditions. The visibility that rain reduces means that the visual scan that a cautious person would conduct before approaching the water's edge is less informative than under clear conditions. All of the standard cues that allow a human being to assess the safety of approaching water in crocodile country are degraded simultaneously by the same event that has just increased the probability that a large predator is in position at the water's edge. This is not a theoretical risk. It is the mechanistic description of exactly how a substantial proportion of the fatal saltwater crocodile attacks on humans in northern Australia and across the species range have been structured. The victim does not see the crocodile. They cannot hear its approach. They approach the water for a purpose: to fill a container, to cross, to fish, to check a boat, because the task they are doing requires them to be near the water, regardless of the weather. And the crocodile is already there. The management response to this understanding at the public health and communication level has been somewhat uneven. Parks and wildlife authorities in the Northern Territory have maintained an extensive signage program at water access points in crocodile habitat that includes specific rainy weather warnings. And the standard advisory to stay away from water during and after rain is included in most of the official communications directed at tourists and visitors. The challenge is that the people most frequently affected by saltwater crocodile attacks are not tourists. They are residents of remote communities who have lived in crocodile habitat their entire lives and who approach the water for practical reasons in conditions including rain, not because they are unaware of the risk, but because the alternative, not accessing the water source, is sometimes not a realistic option. The gap between what the formal risk communication says and the conditions under which people actually interact with water in remote northern Australia is wide, and it is a gap that the rain ambush understanding should be actively informing, in partnership with the traditional knowledge frameworks of the communities concerned, rather than being addressed primarily through signage designed for tourists at boat ramps. The broader conservation context of saltwater crocodile management in Australia adds a layer of complexity to the human safety discussion that cannot be cleanly separated from the biology. Saltwater crocodiles were hunted to near extinction across their Australian range by the early 1970s, when federal and state protection brought hunting to an end. The population recovery since then has been, by the standards of large predator conservation, extraordinary. From an estimated Australian population of perhaps 3,000 to 5,000 animals in 1970, the saltwater crocodile population in northern Australia has grown to an estimated figure of between 100,000 and 150,000 animals. The population is at or approaching the carrying capacity of the available habitat in many parts of the Northern Territory, and is continuing to expand in range in parts of Queensland, where it had been essentially absent during the period of hunting pressure. The recovery is a conservation success by any objective measure. It is also a documented contributing factor to the increase in human encounters and attacks that has occurred over the same period. The Northern Territory attack record shows a clear correlation between population recovery and attack frequency, with fatal attacks being essentially absent during the depleted population years of the 1960s, and increasing progressively as the population has grown. The population is now roughly 40 times what it was at its depleted low. The attack rate, while not 40 times higher, has increased substantially in absolute terms. This is not an argument against the conservation success. It is an argument for the honest acknowledgement that a successful large predator recovery in a landscape shared with humans produces a risk increase that needs to be managed with the same seriousness applied to managing the conservation of the species. The Northern Territory government has, at various points, considered and partially implemented management programs that include regulated harvesting of large adult males in areas of highest human use, on the basis that large adult males are disproportionately represented in the fatal attack record, and that reducing their density in specific locations near human communities and water access points might reduce attack frequency without significantly affecting population dynamics or conservation outcomes. The evidence base for the effectiveness of such programs is limited and contested. The political environment for any policy that involves lethal management of a recovered protected species is difficult. The discussion continues, insufficiently informed by the specific behavioral understanding of the rain ambush phenomenon and its human safety implications, because that understanding is still being assembled from the pieces that researchers and field observers are contributing from different directions. What would a fully informed management response to the rain ambush phenomenon look like? It would begin with the honest acknowledgement that the conditions most dangerous to humans near water in saltwater crocodile habitat are not simply proximity to water, but proximity to water during specific meteorological conditions, specifically during and immediately after rain, in the hours of low light at dawn and dusk that frequently coincide with rain events, and at established prey movement corridors and water access points that also serve as high-value crocodile ambush sites. The intersection of these conditions is where the attack risk is concentrated, and the intersection can be described with more spatial and temporal precision than is currently reflected in standard risk communications. It would involve the systematic mapping of high-value ambush sites in areas of high human use, using the telemetry data that already exists for studied populations, and the traditional ecological knowledge of communities whose members know which specific locations in their water systems are persistently dangerous. These sites are not uniformly distributed along creek banks and estuary margins. They are clustered in locations with specific physical characteristics that are identifiable in advance. Targeted management at those specific sites, whether through physical barriers, enhanced signage, community education, or periodic monitoring and deterrence, would be more effective per unit of effort than the current largely uniform approach. It would involve the direct incorporation of weather as a trigger in public communications about crocodile safety, not merely as a generic modifier of general wariness, but as a specific, mechanistically explained driver of elevated attack probability. The message that a crocodile that was not present at this spot yesterday may have moved here in the last 4 hours because of the rain is more specific, more memorable, and more actionable than the message that crocodiles are always present in this area, and you should be careful. The first message conveys the dynamic nature of the risk. The second message, by treating the risk as static, inadvertently encourages the normalization of proximity to water that has preceded a substantial proportion of the attacks in the documented record. And it would involve the honest engagement with what the sensory biology research is revealing about the specific mechanism of the rain acoustic trigger, because understanding that mechanism allows people to make more calibrated decisions about risk in real time. If you know that rain is masking the acoustic signature of a crocodile in the same water you are approaching, and if you know that your ability to detect the crocodile's presence through visual and acoustic cues is significantly reduced in rain, you are better positioned to decide whether the task you are about to perform at the water's edge can wait, or can be done in a way that reduces exposure time and position at the water's edge, or requires assistance that would reduce your individual vulnerability. The saltwater crocodile is not a monster in any meaningful sense. It is an animal, a spectacularly successful animal that has been refining its predatory capabilities for longer than most